Hi guys, can you hear me?
Yeah, we can.
Yes.
Okay. So yeah, something happened with my internet at home, but I have still the mobile internet. Okay. So I'm gonna start sharing a screen, and let's finish the second part of the class. Let me start recording. Okay, it's already recording. So so thanks for Sana for the question. So now I'm going to start now doing this choice under uncertainty. So finally, this is chapter 6. Again, I'm changing a little bit the order, but just follow the order on the new notes. This is going to be the basis for the midterm, okay? So the first thing that we want to do here is when to study choice under uncertainty, which means I want to understand how consumers speak when not everything is completely known, right? So there is some lack of knowledge about the true state of the world. So the typical example is you want to buy insurance, you buy a house by the lake, and sorry, by the river, and you don't know whether it's going to get flooded or not, right? So there are two states of the world. So it's going to rain, it's going to be shiny. So what are the probabilities of each state of the world? So as this model is going to assume initially that you know the probabilities of shiny versus rain, okay? Everyone understands? So I'm going to have, for instance, 50-50, right? So 50 shiny, 50% of rainy. My decision is going to be buy an insurance, okay? So in this case, right, I know half in the 50% half the times I'm gonna get my house flooded. So I want to buy insurance against that. Okay, so how much I'm gonna buy of the insurance? So the insurance is going to be a contract that's going to tell you you get this amount of money in this state of the world. So conditional on raining, you're going to get some money to fix your floor, okay, if it gets flooded. If it is shiny, you get nothing. Irrespective of what happens, you pay an amount, right? So you pay a prime. So what is going to be the prime of the insurance? Say that's going to be the price of that particular contract, right? So you can also have a particular contract that depends on the state of the world as well. So you have some adjustment after the fact. And okay, so we're going to be more precise about that, but that's the problem we're going to face. So mathematically, we have a capital set object, which is a finite set of alternatives. And we have now a probability over this finite set of alternatives, which is usually money, to pretty much a probability that is greater than or equal than 0 or add up to 1. So mathematically, this means that this is a simplex, right? And in particular, I'm going to write this here. So P belongs to the delta Z. Okay, so in this new world, instead of choosing commodity bundles, the consumer is going to choose lotteries. A lottery is a description of probabilities over these alternatives. Okay, so in this particular case, for the insurance example, Z is going to have the amount of money you get in the rainy state and the amount of money you get in the sunny state. And then the probabilities are the probabilities under which you get each amount. Okay, that corresponds, of course, in this case, that your house gets flooded, right, versus not. Okay, so there's going to be probability of getting this amount of money, x set, versus probability of getting this another amount of money, set prime. And of course, the probability distribution has to add up to 1, has to be greater than or equal than 0. We're assuming here a finite set just for simplicity. Then we're going to specialize it. We're going to make it more general to the infinite set. Okay. Okay. So now I'm going to introduce some notation. For any set in the finite set of alternatives, money, right? There is a degenerate lottery that is called delta Z that will give you, with probability 1, that amount of money, okay? So this is a contract that for sure gives you the amount Z, irrespective of what happens in the world. So it's just a degenerate distribution. This happens for sure. Everyone understands? So this is called a Dirac distribution. So it's just some probability mass, okay, on a small set, degenerate lottery. And then I'm going to define some operational lotteries. So take two lotteries, and then take some number alpha between 0 and 1. And now take this combination, what is called a compound lottery. So alpha p plus 1 minus alpha q tells you that the probability of getting amount of money z is basically alpha times p plus 1 minus alpha q. So the idea of the compound lottery is you have some coin that has alpha probability of being heads versus tails. And then whenever it's heads, you get lottery P. And whenever it's tails, with probability 1 minus alpha, you get lottery Q. So you are compounding two lotteries, right? So that's what they're doing. So this is the composition of two lotteries, the operation. Now, what is going to be my choice structure? Remember this from the first chapters. So this is going to be any subset of the probability simplex. So here, consumers are facing a menu of alternatives. That the alternatives here are probabilities, okay? So it's choice over probabilities. So I'm going to tell you already something. I want to remember this. So sometimes people get confused here because there are two objects that live together. The first object is money, right? Or monetary prices or alternatives. This is the set Z, right? Okay. And then I define a probability over them. Okay. Choice is not over Z. Okay. Choice is over probabilities. Now, notice that because you can define these degenerate lotteries, delta Z, your preferences over lotteries are going to induce a preference over money or over alternatives in Z, right? Because I can pretty much learn your preferences over degenerate probabilities, okay? So, but we are choosing over lotteries, okay? And this can be specialized to choice over money. So you like more money than less. But here, the caveat and the formality is that you prefer formally a degenerate lottery that gives you always more money, right, than another degenerate lottery that gives you less money, right? So we're choosing always among lotteries, right? So the object of choice is the delta Z, not Z. Okay, so now we're studying here. We're gonna go back to the rational model, and then we're gonna then study again some behavioral stuff. But first, we're gonna learn the rational benchmark. So we consider a preference relation on the set of lotteries, okay? And we're gonna study a very particular version of rational model. So a rational model is complete and transitive. We all know that. We're not gonna study only a rational model, but also something that is called expected utility maximization. So
Right. I'm trying to understand the first point. So, so the lottery could be, for example, like you can get $100 for 100%, or 50-50, or like $100, sorry, $80 for like what percent, and then $20 for what percent, and you choose over these different kinds of lottery, and those are the
yes,
choices.
exactly.
And the choice corresponds which lottery I picked. And that's
Yeah.
the C. Okay. Right.
Yeah, so exactly, following your example, right? So if you have these two alternatives, which one would you like more, right? So one natural way is, for instance, computing the expectation of it, right? So you have two lotteries and try to take the expected return, right? So the expected return is one particular example of something more general called the expected utility, okay? So expected utility is basically an expectation, so which is basically this summation over what is called a Bernoulli utility, a small u, defined over the set of prices. This is the set of alternative Z. And then I take pretty much this expectation, which means the multiplication of uz times probability of that monetary outcome, sum over all possible outcomes in the space, okay? And this will give me the utility of the lottery P. Now, a particular example that everyone is familiar with is the case where U is just the identity function, okay? If U is just the identity function, therefore just Z, then what is this object here? It's just expected utility, right? So sorry, it's just expectation. So it's the average of the lottery, okay? So if Z is money and U is the identity, this is just the average, okay? So what happens, for instance, instead of being the identity, U is set to the square, right? And imagine, this, you have also negative prices. So the mean of these things are zero. So then actually this utility will depend on the variance, right? So you can here have different models, choosing different U's, small U. So here there are two U's, capital U or big U and the small U. The small U has a particular name and it's called Bernoulli utility, okay? The small U. The small U is utility over money or utility over alternatives in the capital set choices. The big U is utility over lotteries. So we're gonna be interested in the big U, okay? So our preference relation here defined on the simplex, the set of probabilities, is the big U, okay? Now, this model here is transitive and complete, okay? So expected utility is rational, obviously, but is more than rational, okay? Has more properties, okay? So who can tell me what will be the Cobb-Douglas utility for our choices right now? So describe the utility for the following lottery. So let me do this small example. I'm gonna ask one of you.
I have a question. At the
Yeah.
start of this definition for 7.1, I guess, you said little z was an element of x, and here it's little z is an element of z.
Where is X?
At the end of
yeah.
the first line.
Thanks, there's typo. Thanks. Yep. So everything is in terms of Z, right? So here, let me describe this lottery as basically monetary price 10 with probability 1/2, right? And then monetary price 0 with probability 1/2. Okay. So this, the set is going to be 10/0, right? And this is the lottery here, okay? So in particular, I can just simplify it, and I'm gonna write the probabilities as being that the set is described. So with respect to the first entry, set 1 and set 2, right? Okay. So now, tell me what is the Cobb-Douglas utility of this one? Participants. Alexis, can you tell me what will be? Can you hear me first?
Sorry, could you repeat the question?
Yeah, so look at the screen. I'm asking you, what is the Cobb-Douglas utility of this particular lottery?
Z1 to the alpha, Z2 to the 1 minus alpha.
No, the lottery here, the object of choice is the lottery. So it has to be preference over lotteries.
So the probability, so 1/2 times Z1 to the alpha plus 1/2 times Z to the 1 minus alpha.
Well, actually it would be this, right? So close. In particular, I'm gonna write this way, right? P1, right? Which is the first entry of the probability. It's a vector of size 2 to the alpha, some parameter, right? Maybe you say that, but maybe I mishear you. But here, actually, the set doesn't enter anything, right? So that's a Cobb-Douglas of this thing, okay? So the alpha is something, right? So it doesn't depend on the set. That's my point. Okay. So it depends on the piece. Now, this particular one I created right now, right? So this is my creation. It's a Cobb-Douglas. Now, what is the expected utility of this? So this is the famous U that we're using here. So Alexis, can you tell me the expected utility of this one?
Would it be 5?
No, that is the expected value, the expected utility. So in particular, you know, it's P1, right? The small u of, in this case, 10 plus P2 u of 0, right? So in particular, this will be 1/2 u of 10 plus 1/2 u of 0, okay? This is expected utility. Got it?
Please, Professor, what is V of P? I'm kind of lost.
Sorry?
What is that V of P?
Is an example of non-expected utility, right? So it's a Cobb-Douglas that I created that is representing a transitive and complete preference relation over lotteries. Okay.
Okay.
My point is that both are rational, both are transitive and complete, but they are different, right? So what is the difference between them? What is the difference between them? So think in terms of a little bit what you already know this from the commodity chapter, right? Chapter 3 of Mascolet. So what is the difference between a Cobb-Douglas and a fully additively separable utility? So remember substitute complements? How do you call things that are just additions?
Substitutes.
Substitutes, right? So how come we use this perfect substitutes model here? Why this is the main model we're going to study? So lotteries, right? Why do we use the perfect substitutes? So again, everyone understands what I'm saying? So first model, right, is a Cobb-Douglas model. So Cobb-Douglas allows for some substitution, right? And between the two states of the world, P1 and P2. The second one is perfect substitutes, right? So each probability of each state of the world, I don't care, I don't have any particular attachment to them. I'm gonna attach more utility to the state of the world according to the monetary price it is associated with, okay? According to the Bernoulli, okay? So this is the weight I'm giving to the particular state of the world. 1, 2, the money that I'm gonna get pass through the utility, right? So the money is mapped to utilities through the U function, the Bernoulli, small u. So one is perfect substitute, the other is not perfect substitutes, okay? So what is the idea here? So this model, as I'm telling you, is not only rational, but is more than that, is this perfect substitute version, which is called expected utility. And this model, you know, is proposed originally by von Neumann and Morgenstern in their introduction to the theory of games, because they wanted to model strategic interactions, and they needed a very simple model that allow individuals to take into account uncertainty about the actions of other players, right? So here, the states of the world are actually actions that the other players may take, okay? So initially, as most things in econ, people choose the expected utility, von Neumann and Morgenstern, because it was tractable, mathematically easy, right? So how do you deal with a very complex model where an agent is choosing the best possible action, right? Conditional on uncertainty about actions of other players, right? So I have to aggregate this value of actions according to these different, in this case, uncertainty about the strategic behavior. So the simplest model possible is a model of perfect substitutes, right? Where I have full linearity, additivity, and therefore the expected utility model was born. Okay, the second way to know why this model is so important is because a very natural way people use to rank lotteries is, of course, moments of the distribution, right? So the mean, the expectation. So how do you rank two stocks? One way is to compute the average return, right? And then you compare it. So the average return is a particular example of this expected utility, where U is the identity, right? Another is to compare the risk of the assets, right? So normalized asset and so on with mean zero. If you replace the U by a curve thing, a quadratic U, you can get something that depends on the variance, okay? So this expected utility is, of course, related to moments, and that's also something people use to compare distributions. But the Cobb-Douglas, a little bit, if you look at it, looks a little bit like a likelihood, right? So why not compare, for instance, lotteries according to the likelihood, okay? So I'm gonna give you yet another way you can compare two lotteries, right? So this is gonna be, okay, these are two examples, Cobb-Douglas and expected utility. So now I'm gonna give you now preferences over lotteries. So that are not rational. The first one okay. The first one is going to be a stochastic dominance. Okay. So the first thing I'm going to do is define a cumulative probability, right? So the probability that pretty much the random you have that the value y is less than equal than a random variable y, and this is just the sum of this object here, right? So you have here less than equal than the states of the world, right? Have that this set is greater than equal than set times the probability of this set over all the states of the world. So this y is going to be related, random variable y is going to be distributed with probability p, okay? So this is just the summation over all instances such that the money you get is greater than equal than the number y, okay? And in this finite set of alternatives, this is just a summation, okay? Everyone agrees? This is an indicator function. It gives you 1 whenever the number set is greater than equal than the number y. Else, it gives you 0. Okay, so I'm gonna define this. I'm just gonna call it Fy. Okay. And now take another random variable, right? Now this one is gonna be random variable x with probability q, right? And the same thing. So I'm gonna define this object here. So I'm gonna copy this part with respect to q. Okay. So now imagine you have 2 lotteries, right? And these lotteries, I'm gonna give you an example with the ones that I have with the example 3. So again, let's say now that the space is the space is 10, 0, right? And now I have that p, the first probability gives you with probability 110, and with probability 0 the other one. And now I have q that gives you 0 with $10 and with probability 1, 0. Okay. So you know, take the which one here. There is a clear way to rank these guys, right? So which one will be objectively, quote unquote, better? P or Q? So obviously P is better than Q because this object here is giving you for every is giving you always with higher probability in every state of the world more money, right? Okay, so Q is first order stochastic dominant. To Q, right? So in terms of the cumulatives, you can easily check, right? So I'm going to ask you, one of you, what would be the relation? So Brice, can you hear me?
Yes, Professor.
So if P is first order stochastic dominant with respect to Q, what does it mean in terms of the cumulatives?
It means that for all y, f
Yep.
of y is smaller than f of p, of f of x.
This is smaller, right? For every y.
Yeah.
That's the quantifier, right? Okay. So we're gonna go back to this, but one thing I want you to realize. So this relation that I'm gonna call here first order stochastic dominant. So this is P. This relation here is a binary relation that is incomplete, okay, but transitive. Okay, so this relation here is a natural way to compare probabilities, but it's not a rational one because it's obviously incomplete. Okay, so that's the part is missing, but it's actually a transitive relation. Okay, so what I'm telling you, right, is that whenever we're trying to understand how individuals choose among when you are facing uncertainty, there are many choices to think about this, right? But for many reasons, historical reasons, basically, economists focus on one way, which is this expected utility model. Okay, so I'm telling you a little bit why do we do this? The first reason, historically, was tractability. So doing math without expected utility in game theory is very difficult, very challenging. Now people kind of take him as given, and now everyone tries to do, finance, macro, and of course, also choice under uncertainty in general, using just expected utility. So it became the main model. But this model is a very special case of rationality, right? So there are many other models that are rational. And there are even other models, such as first stochastic dominance, that are not even rational, that are more natural than that, right? So I just want you to have that in perspective. So we are studying a very, very particular model of rational behavior in this world, right? And it's basically because of historical reasons. And what is the missing axiom that makes this model so special? What is beyond transitivity and completeness that makes this model so special? And then I'm done with the class, is the independence axiom. So you have three lotteries, P, Q, R. You have an alpha. P is better than Q. And this will imply that if I take a compound lottery of P and R and Q and R, I still have the same preference relation over the compound lottery. So in a way, the lottery R enters additively, right? So is this additive separability? Is this perfect substitution that is happening here? Okay, so I'm going to stop the recording there. I'm going to take questions.